Today we begin learning CUDA, NVIDIA's parallel programming platform that allows us to use graphics processing units or GPUs for general purpose computing. Before CUDA, GPUs were mainly used for graphics rendering. CUDA transformed GPU into massively parallel processors capable of accelerating scientific simulations, machine learning, image processing, and many other applications. Modern applications often require massive computational power that traditional CPUs cannot provide efficiently. CUDA is NVIDIA's parallel computing platform that allows developers to harness the power of GPUs for general purpose computing. Traditional CPUs contain few cores, 4 to 32 typically. For example, a CPU may have core 1, core 2, core 3, core 4. They are optimized for sequential execution and excellent for complex control logic. The question is why GPUs are different. GPUs contain hundreds to thousands of cores as shown here. Instead of having a few powerful workers, a GPU has thousands of smaller workers. Given two arrays with 1 million elements each. We want to add these two arrays element by element and store in C, in array called C. Effectively, we carry out addition operation for 1 million times. Add one element at a time. CPU adds one element at a time. In GPU, thousands of additions are carried out simultaneously by smaller workers. This illustrates how GPU computation differs from CPU computation. Let's start with a very important question. What is CUDA? CUDA stands for Compute Unified Device Architecture. It is a technology developed by NVIDIA that allows programmers to use GPU for general purpose computing, not just graphics. Think of CUDA as a platform and programming model that lets us write programs in C or C++ and run parts of those programs on the GPU. Traditionally, C and C++ programs run on the CPU. With CUDA, we can keep the CPU code and add GPU code to accelerate computationally intensive tasks. So in simple terms, CUDA is equal to C, C++ programming plus GPU computing. Now that we know what CUDA is, let us look at some real-world applications where CUDA is used. One of the biggest areas is artificial intelligence. Modern AI systems, including deep learning and neural networks, require billions of mathematical operations. CUDA allows GPUs to perform these calculations much faster than traditional CPUs. Another major area is scientific computing. Researchers use CUDA for tasks such as weather simulation, where enormous amounts of atmospheric data must be processed, and molecular dynamics, which studies how molecules interact at the atomic level. CUDA is also widely used in finance. Financial institutions use GPU acceleration for risk analysis, helping them evaluate large numbers of market scenarios quickly. In computer vision, CUDA powers applications such as object detection in self-driving cars and security systems, as well as image filtering and enhancement used in photography and video processing. As you can see, CUDA is used in many fields that require high-performance computing and large-scale data processing. Now let us move into the CUDA programming model, which is the foundation of CUDA programming. Before writing any CUDA code, we need to understand two important terms, host and device. On the screen, we have a simple diagram showing the relationship between them. The host refers to the computer's CPU and system RAM. This is where a normal C or C++ program begins execution. The host is responsible for managing the program, allocating memory, launching GPU work, and handling input and output. The device refers to the GPU and its own memory, often called device memory or GPU memory. The device is where massively parallel computations are performed. Notice that CPU and GPU have separate memory spaces. They do not automatically share memory. Data must be transferred between them through the PCIe bus, which acts as the communication link. A typical CUDA program follows this pattern. Allocate memory on the host, allocate memory on the device, copy data from the host to the device, execute computation on the GPU, copy the results back to the host, display or use the results. Think of the CPU as the manager that organizes the work, while the GPU is the large team of workers that performs many calculations simultaneously. Now that we understand the host and device, let us look at the basic structure of a CUDA program. Most CUDA programs follow the same 5-step workflow. Step 1. Allocate memory. First, we allocate memory for our data. Typically, memory is allocated on both the host and device because the CPU and GPU have separate memory spaces. Step 2. Copy data to the GPU. Next, we transfer the input data from host memory to device memory. This allows the GPU to access the data it needs for computation. Step 3. Launch the kernel. Once the data is on the GPU, we launch a kernel. A kernel is a special function that runs on the GPU. Instead of executing once like a normal function, it is executed by many GPU threads in parallel. Step 4. Copy results back. After the GPU finishes its computation, we copy the results from device memory back to host memory so the CPU can use or display them. Step 5. Free memory. Finally, we release any memory that was allocated on both the host and the device to avoid memory leaks and free system resources. So, the overall process is allocate memory, copy data to GPU, launch kernel, copy results back, free memory. This workflow appears in almost every CUDA application, whether we are doing vector addition, image processing, scientific simulation, or AI computations. What is a kernel? Now let's talk about one of the most important concepts in CUDA programming, the kernel. A kernel is simply a function that is executed on the GPU. Here's a simple example with a global keyword followed by the function signature. And inside the function body, we have a statement int I equals to and ci equals to ai plus bi. Let us break it down. The keyword global tells the CUDA compiler that this is a kernel function or this function is a kernel. What does that mean? It means two things. It means the function is called by CPU. Sometimes CPU is also known as host. And the function is executed GPU, also known as device. So unlike a normal C++ function, a kernel runs on the GPU, so it can be executed by many threads at the same time. Inside the kernel, notice this statement. Each thread has its own unique thread ID. This allows the different threads to work on different elements of the data. For example, thread 0 computes C0. Thread 1 thread 2 computes This is how thousands of operations can happen simultaneously on the GPU. All these things happen at the same time. Now let us talk a little bit more about kernel launch syntax. How we launch a kernel. The syntax look a little unusual. This is the name of the function, and you put these three angle brackets and one number, comma, 256, closing angle brackets, and three arguments. This is the function invocation which actually launches that kernel. And notice this three triplet angle brackets. It means that this is a CUDA's special kernel launch syntax. At this point, let me ask you a question. What does this number mean? Okay, the answer is there's going to be one block, and there's going to be 256 threads in that block. So the launch will create one block and 256 threads. Now we are going to learn what is probably the most important concept in CUDA programming, the thread hierarchy. CUDA organizes work into three levels. One is grid, block, and thread. So a block has a number of threads, grid has a number of blocks. Think of it like a company. Grid is the entire company. Each block is a department. Each thread is an employee doing actual work. The GPU executes thousands of threads, and CUDA uses this hierarchy to keep everything organized. Let us look at a diagram. We have a grid, and we have block, we have another block, and inside these blocks we have thread 0, thread 1, thread 2, and in this block as well we have so in this block, in block 0 we have thread 0, 1, 2, and block 1 we're going to have the same zero. So notice something important here. Thread numbers start at 0 inside each block. This means that block 0 has thread 0, thread 1, and thread 2. Block 1 has thread 0, thread 1, and thread 2. So our thread's identity depends on both its block number and its thread number. So how do you actually identify the thread? That is another question we're going to address here. So let me write the title. Thread identification. CUDA provides several built-in variables that help each thread determine who it is, such as thread idx.x, block idx.x, block dim.x, .x. So let us discuss each of these. Thread idx is it gives the thread's position inside the block. Like in this case, it's going to be 1, 0, 2. That's going to be the thread idx. Block idx is block's position in the grid. So in this grid, entire grid, block idx for this block would be 0. Block idx for this block will be 1. And block dim is the number of threads per block. So in this case, 3 and 3. And grid dimension, the number of blocks in the grid. That means in this case we have 2 blocks. So 2 is going to be grid dim.x. And these variables are automatically provided by CUDA. We don't create them ourselves. Now with this, we are ready to discuss another thing, which is how to find out an index of the thread globally. For example, this thread should be identified globally. This thread should have its unique identifier, something to identify it globally when looking from the global perspective. And this thread should have something to identify, and there should not be conflict between this thread and this thread. They have to have a unique identifier. So we call that process as that formula to compute that global identifier is global index formula. Now, this is the most important formula in introductory CUDA programming. So the formula is you can compute that index, global index, by picking block ID and multiply that with block dimension, and add a thread IDX thread ID to it. Now every CUDA programmer memorizes this formula. Why? Because it gives every thread a unique global index. Even though thread numbering restarts inside every block, like in this case, this formula computes a unique position across the entire grid. Now let us look at an example. Let us calculate the global index together. Suppose we have 2 block IDX 2, 256, 10. Now if you substitute this in this formula, so you replace this by 2, you replace this by 256, and you replace this by 10. So now we have 256 times 2, which is 512, plus 10, 522. This means thread 522 is responsible for processing the element 522. For example, C 522 equals to A 522 plus B 522. Every thread, let me just show this up. So C522 equals to A522 plus B522. So every thread calculates its own index and works on its own piece of data. Now let us look at an example kernel, the formula inside the real CUDA kernel, even a little bit more realistic than the formula I discussed previously. So global keyword, add the vector of floating point numbers, vector A, B, C, and number of elements in the vector. So we need to identify the this index to compute the summation. So int I equals to x times plus and if I is less than n, then we do the summation Ci equals to Ai plus Bi. So let me just scroll down so that you can see it. So we have this more realistic function, a kernel. So this is the function for adding the elements data from this array and this array and writing that data into this array. But this is a function, as I told you earlier, it is launched. It is a function executed in the GPU, and This operation is executed in parallel at the same time. So again, just to explain it further, we have this is the global keyword. It tells the CUDA that the function is kernel. It is called from the CPU but runs on the GPU. And these are the function parameters. These are the pointers which point to the arrays stored in GPU memory. And this is a number of elements in these arrays. Now this is the global index calculation. Each thread computes its unique index. For example, thread 0 will have the value of I equals to 0. So thread 0 will actually work on element 0, first element of this arrays. Thread 1 will get I equals to 1. So second thread will work on the second element of this arrays, and so on. Now this is the if condition to check the boundary. This prevents threads from accessing memory beyond the end of the array. Suppose we launch 1024 threads but only have 1000 elements. The last 24 threads would be out of range. So this check keeps the program safe. Now this is the actual computation. Ci equals to ai plus bi. Each thread adds one element from A and B and it stores the result in C. Since thousands of threads execute simultaneously, thousands of additions can happen in parallel. Now, next thing to talk is memory transfer. Let's discuss how data moves between CPU and GPU. So to copy the data from CPU to GPU, we use a function like this. Here, HA is the host memory and DA is device memory. Data is transferred. The purpose of this function invocation is to transfer the data from CPU RAM to the device GPU memory. So, and to copy the results back after the computation is finished, we can use this. We can call the same function. And by the way, you also need to copy the content of array B as well, not only A. And when you to copy it back, we have host from array C to the device C to host C, and the size and same thing. I mean, copy from in this case device to host. Now the transfer goes in the opposite direction in this case. The results move from GPU memory back to CPU memory. Now that we understand how CUDA organizes threads into grids and blocks, let us look at how GPU actually executes those threads. Here I explain why GPUs can run thousands of threads efficiently and what factors affect performance. By the end of this part of recording, you should understand uh, SIMT, WAPS, scheduling, occupancy basics. First, let's begin with SIMT. CUDA uses a model called SIMT, which stands for single instruction and multiple threads. This is a very simple idea. So we have one instruction that is being executed by many threads. So GPU executes many threads and all performing the same instruction but on different data. For example, if we have a vector addition example equals to AI plus BI, and one thread will compute this thing equals to A0 plus B0. Another thread will compute index 1 element, and another thread will compute and so on. So the instruction is identical for every thread, only data changes. This is what makes GPU extremely effective for data parallel workloads. Next thing we want to discuss is WAPS. And this is the most important execution concept in CUDA. WAPS is a basic execution unit of GPU. Its size is 32. That means warp actually is a group of 32 threads. Many beginners think GPU schedule individual threads, but that is not the case. GPU actually schedules warps. That means GPU actually sets a group of 32 threads into execution together. So the question that can arise in your mind is, if GPU schedules warps, then is it true that total number of threads in the block must be integer multiple of 32? Right? I mean, if the GPU is to execute in the blocks, so one block 32 or 32 times 2, 32 times 3. So the answer to this question is it would be nice if it is a multiple of 32, but that is not required. Since GPU schedules 32 threads, so if it is not multiple of 32, some of the threads may be wasted or not utilized, but that is not illegal, or that is not something prohibited. So you can have threads with a number, let's say 25. You can have total number of threads 50, total number of threads 45, and so on. We will make ourselves clear about this in the next upcoming topics. Let's move on to next topic, which is visualization. So how threads are grouped, and this will also answer the question I asked previously. This question. So we have suppose we have WAP 0, with threads. It has a group of 32 threads, so thread number 0 to 31 will belong to this block warp, and warp 1 has thread 32 to, let's say, 63. Warp 2 has thread 64 to 95. So if we launch 96 threads in total, then GPU will actually automatically divide into 3 warps. Warp 1, warp 0, warp 1, and warp 2. The scheduler works with these warps, not with individual threads. Right? But if the thread is not 96, let's say 98, then it will have to have another warp 3 with thread 96 to, let's say, 98. So the capacity of this warp will be not totally utilized. The computation is wasted in this case. Now let's understand it through an analogy. So think of a warp as let's say 32 students reading together in the classroom. The teacher reads one instruction. All 32 students follow along simultaneously. This works very efficiently because everyone is doing the same thing. Now there's another concept called divergence of warp. You need to be aware of that. Problems occur when threads within the same warp take different execution paths. For example, if we have this situation, if x is 0, then do task A, else do another task. Some threads may execute depending on the value of x. Some threads may execute this function, some threads may execute this function. Now GPU cannot execute all 32 threads together. Instead, it must execute one path first and then the other path afterwards. This situation is called warp divergence. To understand it through analogy, which is similar to this one, you can imagine we have again 32 students reading the same page together. Everything is efficient while everyone follows the same pace. But suddenly, say half of the class to read chapter 1, chapter 2. Then the teacher cannot teach both chapters at the same time. Teacher has to teach both groups separately. The class slows down. This is exactly what happens during warp divergence that I mentioned here. Now next topic to discuss is thread blocks. Blocks are designed to be independent, and one block should not depend on another block. This design provides two major advantages. One is scalability, and another is scheduling flexibility. The same CUDA program can run on different GPU models because of the thread blocks. A small GPU may execute a few blocks at a time. A large GPU may execute many blocks simultaneously. Your code does not need to change. Right? That is the advantage. And about scheduling flexibility, the GPU scheduler can run blocks in any order it chooses because of the thread blocks. This gives a hardware freedom to maximize the performance. So let us discuss an example. Suppose we launch this kernel. Now let's calculate total number of threads. 100 times 256, which is obviously 25,600 threads. So this single kernel creates 25,600 threads. The GPU then organizes these threads into warps and schedules them automatically. Right, now it is time to talk about GPU scheduler. A common question is which block runs first? The answer is that is the job of scheduler. Scheduler decides. So it determines which blocks to run, which warps to run, and when they run. As CUDA programmers, we specify the work. Hardware decides how to schedule it efficiently. That is how scheduler works. Now next we talk about occupancy. This is another important concept in GPU. Occupancy measures how many warps are active compared to the maximum number of GPU compared to the maximum number the GPU can support. So I mean, if you want to see how many, if you have to measure how many are active, I mean, you can formally define this as follows: is equal to maximum number of warps available divided by the active warps. Think of occupancy as how busy the GPU is. Higher occupancy often helps performance because while one warp waits for memory, another warp can execute. However, higher occupancy is not always equal to higher performance. This is a useful guideline, not an absolute rule. Now, finally, practical advice in using these things. When choosing block sizes, use values that align well with the warp size. This also attempts to answer the question I asked before here, right? So you select the block size, so it is in alignment with the warp size. So good choices of the block sizes are 128, 256, 512. Why? Because all are multiples of 32. They divide cleanly into complete warps. For example, 256 threads divided by 32 is 8. And if you divide this, it should be 16. And you should have half of this warps, right? So you choose the size of the block. Let me have the thing you place here to be kind of multiple of 32. So, and avoid unusual values, something like this, 17 or 43 or 91 or something like that. These create partially filled warps and usually waste hardware resources. So as a beginner programmer, block size of 256 is often an excellent default choice. That's the reason why we have this value used in our examples. Now that we understand how CUDA programs execute on the GPU, let's look at what happens before execution, the CUDA compilation process. By the end of this section, you should understand what is NBCC, how CUDA compiles CPU and GPU code, the compilation workflow, and what PTX is. You do not need to become a compiler expert, but it's important you understand the big picture. So first we talk about CUDA compiler. Unlike the normal C++ program, CUDA program contains code for two different processors. CPU and GPU. So when compiling the CUDA, two different processes must be considered. CPU executes host code, and this is for kernel. Because we have two different targets, we need a special compiler, and the name of that compiler is this one, NBCC. The CUDA compiler is called NBCC, which stands for NVIDIA CUDA compiler. Its job is to process CUDA code, CUDA source files, and generate executable code for both CPU and GPU. Think of NBCC as a manager coordinating two separate compilation jobs. One for CPU, one for GPU. Now let us see compilation flow. The flow is something like this. First you have a CUDA file with extension CU, and then it goes down, and NBCC compiler works on it, and it actually works on CPU code, and GPU code. A single, so we have a CUDA file, and then NBCC works on this file, and it actually works on CPU code and GPU code. A single CUDA source file contains both host code and device code. So you put CPU code, GPU code together in a single .cu file. Compiler separates them and send them through different compilation paths. Example: suppose we have a file, let's say named, this is the name of the file, and .cu is extension. Inside the file, we might have host code in C++ and CUDA kernel code. Both type of code exist together in the same file. For example, we can have something like this. This main function is C++ code, and we can have different C++ instructions, and there could be CUDA instruction, syntax instruction to call this function called vector. But before that, let me have the kernel defined. So in the kernel you can have parameters and instructions inside, and you call that kernel. You put the things here and you call like this. If it receives the primary, you also need to pass the arguments. So the host code, this course runs on the CPU, but this kernel, when it is, this will actually launch the kernel, and that kernel gets executed in GPU. We'll come to this how to implement in a moment. Let me see compilation command, how to compile. Once you have a file, a vector add.cu with this kind of code in it, and how do you do the compilation? So to compile CUDA program, we typically use NBCC and the name of the file, source file, and output file. So NBCC is a compiler, CUDA compiler. This is a source file, and this is output executable file. This command starts the entire CUDA compilation process. Now, what happens behind the scenes? Behind the scenes, several things happen. First thing is extract the host code. So NBCC identifies the regular C++, C and C++ portion of the program. And these parts, these are the parts that will execute on CPU. And in the next step, NBCC extracts the device code, and these are intended for GPU. In step 3, compile, and they are compiled separately. These two things, identified things, they are compiled separately. So you can see this as a pipeline, a compilation pipeline. CPU code and GPU code, they run together. So this code is also called host code, and this is called device code. Then finally, once it is compiled, and NBCC will combine everything into so in step 4, NBCC combines everything, into a single file. So it contains CPU executable code as well as GPU executable code. So all packed together. This is the compilation process. Now let us look into binary file. I mean, what kind of binary file does it generate? So GPU portion may contain PTX, something called PTX file or machine code. So depending on the compilation options, GPU architecture and architecture, GPU binary can be of these two types, PTX and machine code. PTX stands for parallel thread execution. It is an intermediate representation. So kind of similar to assembly language. If you're familiar with the assembly language, you can see this as assembly language. So now it has to be ultimately converted into the machine code, but PTX allows NVIDIA to support multiple GPU generations without requiring developers to write the CUDA programs. And some examples of the PTX, the examples of things that you can see in the PTX would be LD global. I mean, kind of assembly language and PTX language instructions, ADD F32, something like this. So this is for load the data. It says to load data from global memory, and this says add two 32-bit floating point values. And this is to store back. So these are much closer to harder instructions than C++ code, high-level programming. As CUDA programmers, you usually do not write PTX code yourself. You write in CUDA C++. The compiler will generate PTX automatically. Therefore, as a student, you only need awareness of PTX. You just need to know that it is something that is there. It exists. You didn't writing the code in PTX is not within the scope for this course. Now I'm going to be demonstrating writing a simple CUDA program, and I will show that how to execute it. So for that I'm using a Visual Studio Code editor. I don't have anything in this folder, and I will be using the terminal to compile it. So first in the terminal, let me create a file called main.cu. I have chosen the name main, and cu is for the cu is the extension for CUDA files. Now in that editor, so we have this main.cu, I will be working on this file. So we will be needing to use some functions available through standard input output library. So let me include stdio.h, and for CUDA functionality we need to include CUDA runtime.s, which this library actually makes available some functions like function for memory allocation, or CUDA free, or copying, or and some other related functions. And let me have a main function, and you can create a kernel for adding the vector, which receives three arrays, and the size of the array. Here we compute index for that particular thread, plus and if I is less than n, then we do addition C. We put the computed result in the array C equals to AI plus BI. So this is the kernel we want GPU to execute, and as a I'm choosing convenient path here, because ideally when you're running this kind of program you will be having a very big data size, maybe 100,000 elements, 500,000 elements, 1 million, 5 million, 10 million, 20 million data elements. But to make it simple, just for the purpose of demonstration, I'm choosing the size of array equals to simple 5, and total size of the memory space is equal to n times we're actually working with a floating point type data, so memory space required for this array would be float, and we will be using this size variable to allocate memory using the function like CUDA malloc afterwards. And let me create a float array, call it HA, equals to 1.1, 2.2, 3.3, 4.4, 5.5, and equals to 10.0, 20.0, 30.0, 40.0, 50.0. These are two arrays, and we also need the third array. These two arrays will be passed in the first and second parameters, and the third parameter we pass the array, but it will carry the result. So float HC, and it is the array of 5 elements. Now we want to, this is the worst, this is the, these are the arrays which remain in the host portion, host memory, but we also need to have a device pointer just to carry address of the devices, GPU, and float for 3 arrays, and we allocate a memory in device. In the host, this will automatically allocate memory for these arrays, but in the device we use this function CUDA malloc, it's a double pointer address of DA size. Size is the variable we computed here, and we also allocate for another array size, and we also allocate for the third array Now, once we have memory allocated in the device, we need to copy this data into this device A. Array, this array and this array, these two arrays in the device in the GPU. So we copy the data from host to, so for that purpose we use this function CUDA memcopy. So CUDA memcopy DA it's a size and also we copy another array so we have SB and SB. Now this is time because this will actually copy the data into the GPU device. Now we can launch the kernel, so that kernel will actually make use of this data in multiple threads. And I'm choosing one block and 256 threads. These are the device array addresses, so that this kernel will work on the device, the data that is copied into the device. Now you wait for the execution to finish. CUDA device synchronize, and we copy the result back. Now once it is done, and we copy result from this array back to this array. So CUDA mem copy HC DC. The first argument is about the destination, and the second is from the source. This is we are copying from device to host. In this case, size and in the host, this is the host portion of the program. We want to display the result. Using printf. This is a floating point number, %f space HCI. New line at the end of the array. Now once it is done, then you need to, these are the functions. We allocate the memory in the device. You need to free that memory, so you call this function CUDA free. So this is the program we have. Right now I'm going to be moving to the terminal and try to execute this. In the terminal we have this main.cu. So this is the same program we just wrote here, and compilation command is nbcc. The name of the file main.cu, and executable main. It is successful. We have main file created, execution. So it got the 11.1, 22.2, 33.3, 44.4, 55.5. So the values of the array was 1.1, 2.2, 3.3, 4.4, 5.5 in one array, and another array it was 10, 20, 10, 20, 30, 40, 50. So this is as expected. Now that we understand kernels, threads, let me write it. Memory transfers. Let us step back and look at how a real CUDA project is organized and built. Some of the contents in this part of the recording may be overlapping with the coding part I did in just before in the previous part of this recording. But anyway, for the sake of completeness, I will discuss those things here. This will, even if it is kind of repetitive, but it will help to understand it better, I hope. So now, so far, we have written a small file examples, a small code, single file example. But in real application like artificial intelligence, artificial intelligence simulations or image processing, we structure the code like a proper software project. So a typical CUDA project is organized into different folders. So we have project name, and within the project you have a folder called source containing source files. You have include folder, you have kernels folder, you have build folder. So let's quickly understand each folder. This source folder contains the main application code. CPU side logic. This contains header files .h, or sometimes you have also .cuh for CUDA header, and kernels. This folder contains CUDA GPU functions, and compiled binary or object files in the build. So this structure helps separate CPU logic from GPU logic, which is very important in large projects. And some examples of in typical project of examples of the file could be something like this. You can have main.cu, vector head.cu, cuh header file, and this is going to be the main entry point of the program, basically host code, and this file will contain the implementation of CUDA kernel function, and here you put the declaration like in the in the way that similar to how you put C++ programs, function definition, function declaration, and function definition in header file and .cpp files. Now let me talk about CUDA workflow. So basically a standard CUDA execution workflow. This is the same in almost every CUDA program. So step 1, allocate host memory. In host, either you, like in the example we did before, it was static allocation, but for the dynamic allocation we use malloc. In the case of C program, but if you're working with C++, then you may have to use new keyword. This is where input data is created or is stored. In step 2, allocate device memory. So for that we use the function CUDA malloc. This creates a space inside the GPU memory for the array or for the variables you want to work with. Step 3, copy data to GPU. Now you transfer the data from CPU to GPU, and for that CUDA has a function copy, because CPU and GPU have separate memory. This step is mandatory. Step 4, launch kernel. Now we execute the GPU function using the syntax something like this. This is where parallel execution happens across thousands of threads. Then in step 5, we copy the result back. After computation in the GPU, we bring the result, outcome of the computation, back to the CPU. And again, we use the same function to copy back. And final step, step 6, you free the GPU memory. So, and also if you have used malloc, then you also will need to free the host memory as well. So one example of CUDA, I already had an example in the coding practice in this recording, just before this recording. In the previous part of this recording. If you move back in this recording, you will find a coding example exercise, and this is you can see this as a kind of a repetition, or there could be overlapping in the things we discuss here. So example, so you define n if you want to have the size of the array, and you use so this is the address of the device in the GPU, address of array in GPU, address of host element of GPU array, allocate memory, this db will point to the second array, and so this will allocate memory for the third array, and then you use call this function, and then you launch the kernel, device first array, device second array, device third array, and the size. And once it is done, you copy it back. So you allocate the memory, you copy the data into the device from the host, and you launch the kernel. Once it is done, you copy it back, and then you release. This prevents memory leaks and releases the GPU resources. Here's what's happening. We allocate a memory for input and output arrays on the GPU. Copy the input data from CPU to GPU. launch the kernel with 4 blocks and 256 threads per block, perform the computation, copy the results back, and free all GPU memory. And one final thing you should keep in mind is you should be um, skillful or comfortable checking errors, like you might have experienced in C++ programming. If you have done that, you should be very comfortable in checking the errors, because most of the times program doesn't work. In the first attempt, you may have to apply different error checking methods. Two common tools for error checking. That can be useful. One is CUDA T. So this is the type which actually carries the error, and also you can use to see what actually happened in the last operation. This actually helps us detect problems like invalid memory access, kernel launch failures, and illegal arguments. A good CUDA programmer always checks errors after kernel launches. Up to this point, we have been writing CUDA kernels ourselves. We have learned how to allocate a GPU memory, copy data, launch kernels, manage threads and blocks. This gives a lot of power and flexibility. However, for many common operations, writing custom kernels can become repetitive and time consuming. So the question is, why thirst exists? The thirst, the topic we're talking in this part of the recording, why does this exist? The reason is CUDA is powerful. Let me write that question. So CUDA is powerful, but writing kernels for every task is very tedious. Thirst provides a higher level interface. Which is similar to C++ HTL library. So instead of writing a custom kernel every time we want to sort data, add values, and transform arrays, Thirst provides a ready-made GPU algorithms. Think of Thrust as a library that lets you use GPU acceleration with much less code. So let's try to understand it more through HTL analogy. My assumption is that you are exposed to HTL, standard template library of C++. So if you already know C++, the easiest way to understand Thirst is through this library, HTL analogy. On the CPU, we often use the things like vector, short, transform, etc. These are convenient. Move a little bit up so that you can see it. So these are the convenient high-level tools that hide implementation details. Thirst provides very similar tools for GPU. Some examples are Thirst, device vector, short, transform. Notice how similar the names are, right? So device vector, vector, short, short, transform, transform, and namespace is std. In this case, we have Thirst here. This is intentional. Thirst was designed to feel familiar to C++ programmers. Now, let me quickly talk about the comparison between CPU and GPU, because CPU is the one which will be executing these functions, and GPU is the thing that which will be executing these functions. So CPU now for CPU we use these functions. For GPU, the goal is simple. Take STL style programming and bring it to GPU. And the question that may arise is, what are the benefits of using Thirst? So why the developers use Thirst? One of the reason is less code. Many operations that require dozens of lines of CUDA code can be written in a single line using Thirst. Another is improved readability. Code becomes easier to read and understand. Instead of focusing on thread indices and kernel launches, we focus on the operation we want to perform. And third advantage is rapid development. Developers can build GPU applications much faster because many common algorithms are already implemented and optimized. And it also provides very commonly used algorithms, so that makes it very convenient to just pick and apply. Such as short, transform, let's briefly discuss each one. Short. Purpose of short is to short the data on the GPU, and the way you use it is right. It's kind of similar to STD short for CPU. And another, reduce. It combines many value into single value. For example, if you have so the purpose of reduce is to combine this into single value. Okay, so 7, 21, and this is a reduction operation, and the syntax is going to be same. Only difference is this thing, you change from std to thrust, and also you look into the prototype of the function. Transform. The purpose of transform is to actually transform the data into a different one. For example, if an element is, let's say, x, then you transform each element to x square. Something like this, right? That is a transformation. And the purpose of scan is to compute cumulative sums. For example, if you have something like this 1, 2, 3, 4, then you compute the cumulative sums, right? Sums, like in the first case it is 1, and second case you add these two things, 2 plus 1, 3. In the third case you have 3 plus 2 plus 1, 6, and here 6 plus 4, 10. So this function will compute this thing from this as an input, and it is widely used in parallel algorithms. Next, copy. Purpose is to copy the data between containers. And fill. It fills a container with a same value. Container or its elements with the same. So an example of fill would be if a container has let's say 0, 0, 0, 0, 0, then you want to fill it with some value 1, 2. Now the most important thing to remember here is with raw CUDA we tell how to do the work. With thirst, we often tell GPU what work we want done. So it's a difference between how to do it versus what to do it, what we want. Now that we know what thirst is, and why it exists, let us write our first thirst program. You will notice that using thirst feels very similar to using the C++ standard template library or STL. In fact, you will use std vector and std short. You will feel right at home. Including thirst libraries. In a code, when you write a code, you should include the necessary libraries. So like any C++ program, we first include the headers we need. For thirst tools, we need include. Now let's understand this. So this gives GPU based vectors, and this gives GPU sorting algorithm. Just by including these headers, we gain access to powerful parallel operations running on the GPU. Creating a device vector. Next step is to create a device, a vector is stored in the GPU memory. The purpose is to create a vector in GPU memory. So for that, you can use this syntax. So if you compare this with C++ syntax for creating vector, is pretty similar. This creates a vector containing 5 integers, and notice this thing, device vector. It device tells that the data is stored in the GPU, not CPU memory. Think of it as GPU equivalent of this thing from C++. Now, how to copy data into this vector? Next question. You can access element in the same way that you can use to access element of the C++ vector. B1 equals to 5, B2 equals to 8, B3, scroll up a little bit just to make it visible. V3 equals to 2 equals to 1. So at this point the vector contains 10, 5, 8, 2 and 1. For learning purposes, we are assigning values one at a time. In larger applications, data often comes from files, not like this, from computations or other containers. Now, how to do sorting? To sort these values, you can use this function, and you want to provide the first element you want to sort from, b.begin. The syntax is pretty similar to the C++ STL library syntax. This is the invocation of sort function and looks very similar to STL. This begin points to the first element of B, and points to the last element. It's not last element; it is one past last element that will come after this element. So together they define the range of the data to be sorted. When you call thrust sort, thrust launches optimized GPU operations behind the scenes. So we didn't write a kernel, just remember. We didn't calculate the thread indices in this case. We didn't choose block sizes. Thrust handled all of that for us. So let us see the result. Now, to demonstrate this sorting, let me quickly switch to the coding part. For coding, I'm going to be using Visual Studio Code and the terminal to execute the code. So the code for source program, you use the same extension like CUDA.cu. I'm using this main.cu file, and you need to include, like in the C++ other programs, you need to include the library source slash for sorting operation. And also, if I want to use just to display the data, I want to use stdio.h. So here, first we need to create a vector. To store integer type, vector has a size 5. It will actually create a vector in the device itself. Device vector, I think there are 2 underscore characters, so I'll remove 1. And you initialize the elements. 10 first element, b1 equals to 5, b2 equals to 8, b3 equals to maybe yes, equals to 2, b4 equals to 1. We want to sort this this data. I just want to make sure everything is correct. Okay, here first device vector, devic device vector. Yeah. Now to sort, we want to use the sort algorithm that I mentioned before, and the range b dot begin, b dot end. Now it will do the sorting. There's no, I mean, you don't need to copy allocate memory in the device. You don't need to copy into the device. It just works automatically. Now to display this, I'm using this printf function available through this library in a loop. I equals to 0, I less than b dot size of the vector, I plus plus, and printf integer printf new line character. Now you don't need to release memory, you don't need to allocate memory. This is the code I'm going to be running in the terminal. Switching to the terminal, we have this main.cu. Remove main, previous main. The content of main.cpu is here. Now compilation main.cu main. So we have a warning, but we have that file created. Let me check the how does this application behaves. There's some problem, so maybe we should go ahead and fix the problem. the warning problem, right? So go back to the code. The warning message is it says that allocate reference. Looks like the complaint is about the type of the data that is fed into printf function. Is line number 18. So probably the type of this this is a little bit different than uh, the integer type expected. So just to avoid that, cast to integer, and just let me double check any problem I may have here. Device vector 5 and b0 1 2 3 4 10 5 8 2 1 short begin to end, and vi integer. I didn't find any issue in this, so let me switch to the terminal and try to compile one more time. Compilation successful without warning. Main. So we are getting the expected result. It is sorted in ascending order 1 2 5 8 and 10. And similarly, if we want to try, let's say, some other example, maybe reduction example. So instead of sorting, if I want to do reduction, then reduction is process of, by default it is addition, so, summation. Therefore sum equals to begin b dot end. So this is since I made, and this for loop will print the original data. So therefore I'm not removing it here. I think it should be okay. Let me go to the terminal. So the reduced value is 26, right? So 15 plus 8, 20, 23, 24, 25, 26. So it is correct to reduce value sum. And we can I think these are the two these examples would be sufficient. We can, if you're interested, you can practice other functions. But the things to note here is that we didn't write a kernel in this case, unlike in CUDA program. Thirst performs the parallel reduction automatically. Think about what we've accomplished. Using raw CUDA, sorting and reduction requires significant code and careful optimization. With Thirst, we simply write the function sort and reduce, and let the library handle the details. This allows us to focus on solving the problem rather than managing low-level GPU execution. By now, we have covered a lot of material today in this recording, and you now have a solid foundation in CUDA programming and an introduction to thrust. Before we finish, let me review the key concepts you should take away from this session. First thing we talked is CUDA fundamentals. In this, we talked about the host and device, and host is a CPU and system memory. Device is a GPU and GPU memory, and these are separate systems that communicate through memory transfers. Next thing is a kernel. You learned that kernel is a function that runs on the GPU. Kernels allow thousands of threads to execute the same operation in parallel. And you learn about threads. Threads are the smallest execution unit in CUDA. Each thread typically processes one element of data. Then we talked about blocks. Threads are organized into blocks. Blocks help structure parallel work and allow threads within the same block to cooperate. And grids. Blocks are organized into grids. A kernel launch creates a grid containing one or more blocks. Then we talked about SIMT. Single instruction, multiple threads. Many threads execute the same instruction while operating on different data. Next, WAFs. You learned that GPU schedules execution in groups called WAFs. A WAF contains 32 threads. Understanding WAFs is essential for understanding CUDA performance. Then we also talked compiling a program or compilation. And BCC compiler. This is a CUDA compiler which separates the host code and device code and compiles them independently and links them together into a single executable. And then we also talked about building a complete application. And in this case, you also learned the standard CUDA workflow. The process: first allocate a host memory, allocate device memory, copy data to the GPU, launch kernels, copy results back, and free memory. And this workflow forms the foundation of most CUDA applications. And we also talked about the thrust fundamentals. And we talked about purpose of thrust, and we talked about STL-like interface. Of the thrust. One of the thrust's biggest advantages is that it feels very similar to C++ standard template library. And then we also talked about device vector tool container. So it is similar to std vector container, but it stores the data into GPU. And we talked about sort for sorting the algorithm, sorting the container elements. We talked about reduce, to combine many values into a single result, such as computing a sum. So finally, if there is one message I want you to remember from this recording, this session is CUDA gives us control over GPU hardware and massive parallelism. Third builds on the top of CUDA and provides higher level tools that make GPU programming faster and easier. As you continue learning GPU computing, you will use both approaches. Raw CUDA when you need maximum control and optimization. First, when you want productivity and concise code. Together, they form a powerful toolkit for higher performance computing.